All right, let's dive into one of the biggest, most mind-bending ideas in the history of science, Einstein's theory of relativity. Seriously, this thing didn't just add a new chapter to the physics books, it threw out the old book and wrote a completely new one, changing how we see space, time, and even gravity itself.
But before we get into all that, let me ask you something a little strange. What if time isn't constant? You know, the steady tick-tock of the clock that we all experience. What if your watch and my watch could actually run at different speeds? Now, that sounds like something straight out of science fiction, right? Well, it's not. It is the bizarre reality that Albert Einstein discovered, and it all began with a single, massive puzzle.
You see, toward the end of the 1800s, physics was kind of hitting a wall. Scientists had this huge problem on their hands. They discovered a universal speed limit, but it made absolutely no sense based on the laws of physics they had relied on for centuries. And that cosmic speed limit belonged to light.
Now, people had been trying to measure the speed of light for a long, long time. Way back in 1638, you had Galileo with his lanterns on hilltops, which, didn't work. Light was just way too fast. Then, in 1676, a guy named Ole Romer got clever and used the timing of Jupiter's moons to get the first decent estimate. But the real earthquake hit in 1887 with an experiment that found something, or rather didn't find something, that changed everything.
So at the time, everyone thought light was a wave, and waves need something to wave through, right? Sound waves travel through air, ocean waves travel through water. So for light, they came up with this idea of an invisible, space-filling substance they called the luminiferous ether. The whole point of that 1887 experiment, the Michelson-Morley experiment, was to finally detect the Earth moving through this ether.
Except they found nothing. Zip. No ether. And this led to a massive contradiction that basically broke physics. According to Isaac Newton, speeds should add up. If you're on a train going 50 miles per hour and you throw a baseball forward at 10, someone on the ground sees it moving at 60. Simple. But what this experiment showed was that light just doesn't care. Its speed is always the same, roughly 186,000 miles per second, whether you're standing still or on a rocket ship. It was a total paradox.
And this is where a brilliant young patent clerk named Albert Einstein steps onto the scene. He looked at this paradox and proposed something so wild, so out there, it was almost crazy. He said, what if we just accept the weird result? What if the speed of light is the one constant thing in the universe? And if that's true, he argued, then other things we thought were constant must not be. Things like space and even time itself.
And that was the key. To make the math work, Einstein had to get rid of an idea that was just common sense to everyone, that time is absolute, that a minute for me is the same as a minute for you no matter what. He realized that for the speed of light to stay the same for everybody, the passage of time itself has to stretch and shrink depending on how you're moving.
Okay, so how on earth does that even work? To help us wrap our heads around it, Einstein loved to use thought experiments. So let's try one of his most famous ones, a clock that keeps time with a beam of light. Okay, picture this. You have two mirrors, one above the other, and you have a single particle of light, a photon, bouncing perfectly straight up and down between them. Every time it makes a round trip, up and back down, that's one tick of our clock. Simple enough. But now let's put that clock in motion. Let's say it starts moving to the right. From our point of view, watching it go by, that photon isn't traveling a straight path anymore. To get from the bottom mirror to the top one, it now has to travel along a longer diagonal path. And here's the crucial part. We know the speed of light never, ever changes. So, since it now has a longer distance to travel, it must take more time to make the trip. To us, the moving clock is literally ticking slower.
This crazy effect is called time dilation, and it's the heart of special relativity. But that's not all. The theory also says that moving objects literally get shorter in their direction of motion. And it's where we get maybe the most famous equation in all of science, E = mc squared, showing that mass and energy are just two sides of the same coin.
But Einstein knew he wasn't done. His 1905 theory was special because it only worked for smooth, steady motion. It had a huge hole in it. It didn't explain gravity. It took him another decade of brain-twisting work to figure out how gravity fit into this new, bizarre universe he had uncovered.
His big aha moment came from what he later called his happiest thought. Imagine you're in an elevator with no windows, way out in deep space. If that elevator starts accelerating upwards, you'd feel yourself being pushed down onto the floor, right? Well, how is that feeling any different from just standing still on the surface of the Earth? Einstein realized you could not tell the difference. He said they aren't just similar, they are the exact same phenomenon. And if gravity is the same as acceleration, that leads to a conclusion so profound it's hard to even process. Gravity isn't some invisible force pulling things together. Gravity is what happens when mass and energy literally bend and warp the fabric of space and time. Gravity is the shape of the universe.
The classic way to picture this is with a trampoline. Imagine you put a heavy bowling ball right in the middle. It makes a big dip in the fabric, right? Now roll a little marble nearby. The marble will curve and spiral in towards the bowling ball. But here's the thing. There's no force pulling the marble. It's just following the curve in the trampoline fabric made by the bowling ball. That's what planets are doing around the sun. They are just moving in the straightest possible line through a universe that has been curved by the sun's enormous mass.
Physicist John Wheeler summed it up perfectly with this beautiful line. It's a two-way street, a cosmic dance. Space-time tells matter how to move. Matter tells space-time how to curve. The stuff in the universe creates the curves, and the curves tell the stuff how to get around.
Okay, so this is a truly incredible story about the universe. But is it just a story, or is it actually true? Well, the great thing about a scientific theory is that it makes predictions. And general relativity made some really wild predictions that astronomers could go out and actually test.
And one by one, the evidence just kept piling up. If space is curved, then even light should have to bend when it passes a massive object. Well, in 1919, astronomers saw just that, starlight bending around the sun during an eclipse. The theory also said that spinning objects should literally drag space-time around with them, which, amazingly, we've also confirmed. And of course, the big one. In 2015, we finally detected gravitational waves, actual ripples in space-time, from two black holes crashing into each other a billion light-years away. It's just staggering.
But one of the very first big wins for Einstein was solving a tiny little mystery about the planet Mercury. For decades, astronomers had noticed that Mercury's orbit wasn't quite perfect. It wobbled by a tiny amount every century, just 43 arcseconds. Newton's laws couldn't explain it. But when you ran the numbers with general relativity, it predicted that wobble perfectly, down to the decimal point.
Now, all of this stuff about black holes and bending starlight might seem pretty far removed from our day-to-day lives, but believe it or not, you probably use relativity all the time, right from the palm of your hand. Seriously, anytime you use a GPS, you are using Einstein's theories. See, the clocks on those GPS satellites are affected by relativity in two ways. First, because they're moving so incredibly fast, special relativity says their clocks should tick a little bit slower than ours. But because they're way up high where Earth's gravity is weaker, general relativity says their clocks should tick a little bit faster. It turns out the faster effect is stronger. And if the engineers didn't account for both of these tiny time differences, your GPS would be off by several miles within a single day. The whole system would be totally useless without Einstein.
So there you have it. From a puzzle about the speed of light, we end up rewriting our understanding of time, space, and gravity, and even enabling the technology that helps us find the nearest coffee shop. Relativity reveals a universe that is so much weirder and frankly so much more amazing than we ever thought possible. Which leaves us with a final question for you. We know time dilation is real. So, if you could hop on a spaceship, travel near the speed of light and come back to Earth thousands of years in the future, what would you hope to see? Let us know what you think in the comments.